Okay, we're wrapping up our discussion of this question. Why does ice melt spontaneously at room temperature? Be prepared to share. Okay, let's hear from like at least 3 people. What did you and your group talk about? All right, Tara, pick a color.
Pink.
Pink. What did you and your group talk about?
How it's kind of returning to its original state.
What do you mean?
Like if you have like water as originally liquid and it freezes, it's just like returning to its original state. Equilibrium, perhaps.
What makes you call it the initial state? So first of all, when it melts, what does ice melt into? Liquid water, right? So I think what you're saying is we know that at room temperature, water is a liquid, right? Is that a good way to reformulate what you're saying? Okay. I don't disagree with that. Why though? Why is it that the ice is going to return to its natural state, as Tara put it? Jose, pick a color. Orange. Okay, what'd you and your group talk about?
Oh no, I was just gonna say something.
Okay.
Is it because like it takes less energy to like keep it in that state? Like water both sides.
Okay, so elaborate a little bit. So which one requires less energy to stay in? Okay, so Jose puts forth the idea that perhaps H2O. Something like this? Yeah? This is an okay paraphrasing of what you said? Sure? I need you to tell me. Yeah? Okay, so water is like an energetically easier state to exist in than ice. Do we agree with this? Well, Jose, I know you agree with it. You put it forward. Talk at your table. Do we agree with this? Do we agree that it's quote unquote energetically easier to be in the liquid form versus the solid form? Let's do a 10-second combo real quick. All right, let's wrap it up. Okay, raise your hand if you and your group wound up agreeing with this statement. It's okay if you did. It's a discussion. So raise your hand if you think you agree with this statement. Or like if you agree but with a caveat. Like I agree if. Okay, Marco, what's your caveat?
I was thinking like at that temperature it might be an easier state to exist in, like at that room temperature. So but like if it wasn't room temperature, like maybe if it was like freezing, then it would be easier than it exists in the sun.
Okay, so you're recognizing that there's potentially some temperature dependence involved? All right. That seems intuitive to me. How about the dissenting folks, people that disagree? You don't get to be a neutral party here. You don't just get to be like, oh. Pick a side. So, Michelle?
I agree with what you said.
Okay, so you think that this statement is true as long as we're saying at 25 degrees C?
Yeah.
Okay. Any disagreement? Kazuya?
I would agree.
You would agree? Okay. Robin?
Well, I agree because like entropy is like.
Oh, hold on. Yes, but also no.
Well, enthalpy too.
Okay, yes, but also no. We're yes, but we're not there yet. I'm building a narrative.
It's like randomness is like more fun in entropy.
Yes.
It's like water molecules not in solid lattice, so it's gonna like the freedom dispersion. Sorry.
I understand what you're saying. Okay, so Robin, for those of us that are listening back at me shouting at you in the future, so future you, listening to me shout at you through this iPad recording, Robin is bringing up stuff that we haven't learned yet at this point in time. So, if we're not going to use pre-existing knowledge, let's follow our intuition. Is there anybody whose intuition disagrees with this statement? Tara?
I don't know. It's good.
You just feel like it's wrong. Why? Because I'm making a big deal out of it? Yeah, okay. Let's go back to day 1, certainly week 1 of Gen Chem 1. If we had to organize the phases of matter according to most stable to least stable, how would we make that ranking? So we've got solid, liquid, gas. What phase is the most stable? Ivy? So I would probably put this down. Wow, I'm doing geometric drawing so well right now. Okay. Here at the low end of the energy spectrum. Why? Why did you want to put that at the low end of the energy spectrum, Ivy?
Because it's less reactive and it takes in heat to go to a higher form, which makes it more conservative of energy.
Okay, so you're saying these tend to exist at lower temperatures. What else? What other kinds of energy besides thermal energy we talked about today? Enthalpy, which is thermal energy at constant pressure. So yes, but again, also no. Kinetic energy. What do you notice about the amount of free motion available to atoms packed inside a solid structure? Do they move? No. Otherwise, it wouldn't be a solid, right? Solids are incredibly dense compared to the other phases. And the reason why they're dense is because there's a restriction on the amount of translational motion freedom available to those particles in the solid phase. They're all locked together very tightly in either an ionic bond or a covalent bond. So lower temperatures, these tend to have low kinetic energy on a molecular scale. All right, what next? What ranks above a solid? Okay, just above a solid? Is there no intermediate phase? Liquid. So liquids, let's make a similar argument. These are things that tend to exist at like mid to high temperatures. And what can we say about the movement of particles in the liquid phase? Low, but how does it compare to solid? Solid's like basically none. And liquid is some, right? Some non-zero amount. Can't ignore it. Which means then, Iad, the highest energy phase is? Gas. Okay, so we are gaseous. These typically exist at higher temperatures. There's a large amount of kinetic energy, right? That's the whole model of kinetic molecular theory of gases. Particles move fast, smack into one another, that gives us pressure. Now, why am I bringing this up? Jose said that it is energetically easier to, for the liquid state to exist at 25 degrees than the solid state. And I agree with that if we change the terms to be something more specific, but I don't know that you have that language yet. So I'm going to give you a counter argument. Don't things like to be stable? Don't things like to exist at lower energy states? Do you like to be mentally, emotionally, and physically stable?
Of course.
No, Tara's down for some hysteria, it seems. Rad. Okay. But generally, all things tend toward the lowest possible energy state. Do we agree with that?
Yeah.
Okay. Isn't that what this solid is? That's the most stable arrangement of water molecules. It's the one where we've minimized the amount of kinetic energy, minimized the amount of thermal energy. Overall, this is a low energy or stable state. So let's add that here. Existing as a solid is more stable structurally on a molecular level than as a liquid. So this cannot be the full story. All right, let's hear from other groups. Michael, pick a color. Purple.
Calculated. We said that if the ice is the system and the surrounding is the room, then the difference in heat between the system and the surrounding are different. So then they want to try to balance, I think.
Yes, the ice in the room are going to try to reach thermal equilibrium, aka become the same temperature. You leave a cup of ice out, it will eventually melt. Then you come back in 8 hours, it will eventually be room temp. You leave your hot bath for 2 hours, and you come back and it's room temp again. So ice melting is a process that exchanges what kind of energy if we're talking about temperature differences? Thermal energy. How does it exchange thermal energy with the surroundings? Specifically, who's absorbing, who's releasing? What kind of process is this? If we're treating ice as the system, and that system requires heat. Endothermic. Wait a minute, this says this requires external energy in order for this to melt. Is that the definition of spontaneous? No. So we've arrived at an interesting contradiction. The solid phase is typically more stable than the liquid phase, and also becoming the liquid phase is a process that requires energy. So then, what is it about this process of ice melting that makes it one that is spontaneous? In order to answer that question, we need to understand a thermodynamic property called entropy. So this is capital S. Lowercase s is our molar solubility. Capital S is entropy. So Robin, what is entropy?
Well, I kind of just thought of it as like you have it's gonna take and you have a bunch of free energy. You have a bunch of energy, and to when you're in the liquid phase, you have all of your molecules like dispersed everywhere, and that energy is kind of tied up in like trying to like what's the word? It's sorry, I'm trying to say it.
Uh-huh.
Like, but it's just this negative.
Okay.
Sorry.
Robin's in math brain mode. That's fine. Your math brain, I'm sure, is right. Ivy?
All molecules are trying to get away from each other.
That's not always necessarily true.
In gas forms particularly, molecules are trying to get away from each other, and the universe is slowly dying.
Okay, so you're talking about the expansion theory of like the cold dead universe? All right. Entropy is a weird one. Entropy is like our human understanding, or specifically like a value assignment, a quantification of the amount of disorder. Some people might say chaos. But innately, what we call entropy relates to a degree of disorder or chaos.
But I thought it also like was to do with like how much is not worth will not worth or
You are thinking, yes, so Robin's bringing up like entropy is also thought of as like the difference between your enthalpy and something else, and you're right, but we haven't talked about what that something else is yet. Okay, everyday examples of high entropy systems. Okay, I will start. My office. It's a hot mess. I just got stacks of paper with no kind of organizational theme to them at all, piled all over my desk. I've got a dying plant in the corner, a dying plant on the desk, random like plastic ducks just filling my whole space, right? It's a mess in there. Yeah, there's a large amount of entropy in my office. Yes, Ivan?
So you have like gas canister,
Okay, so say we have a gas canister and
cage, and that be like
if we are taking that gas and then doing what in the cylinder? Okay, you're letting it diffuse.
but you have gas in the canister, right? So there's a lot of disorder.
But then we're taking all that disorder and we're like
Keeping it. Oh.
putting it out in the world, right? So what was once contained is now unleashed. So I would say, yeah, like if you're talking about like compressed gas that you can use to clean your keyboard, and you let it diffuse outward, that's causing more chaos. Question, Michael?
No, I was thinking about. Wait.
Thinking about what?
It's like gas.
Yes? No, I want to hear it. Gas diffusion, what about it?
What if fart?
Yes, it would, because what was once localized in your GI tract is now everyone else's problem, right? You are spreading all of that everywhere. Which of these states seems to have more innate organization? The post-fart state is the one that's more chaotic, right? It's a valid question.
Make sure to put that in.
You got it's recorded. It's already here in the notes. I just didn't want to take up the whiteboard space. Oh my God, we talked about a fart in class. Wow.
Normally we don't do that,
Monument.
but nothing wrong with a little chill every once in a while.
All right, another example of a highly entropic state, highly disordered state. That's all we got? Is my office and farts? We can't come up with one more example? Tara?
Like taking like laundry out of the machine.
Or the laundry. That's what you
That's literally what I just said.
Not taking it out, but
That's what I said.
Taking it out of the machine?
Yeah.
I would argue, yeah, right? It's all localized and now it's delocalized. But then what do you do if you're a responsible adult with your laundry? You take it out, you fold it, and then you put it away. It doesn't just get dumped into the laundry chair where you're like, this works. Right? Ivy? Okay, what about the sun?
Well, it's nuclear fusion. Fission? One of those.
Gigantic ball of nuclear fusion, yes.
And the molecules are constantly crashing into each other and breaking apart and making and kind of just creating a lot of energy.
Actually, no, I was in class.
Yes, but let's be specific. So there's two processes here. You're talking about fusion, which is where like hydrogen and hydrogen come together to form helium. Guys, I'm recording this. Let's keep the background noise low, thank you. So is this process here, the fusion process, one that involves a high degree of disorder?
Yeah.
It is?
They have to.
But I'm taking two things and now structurally making it one.
Okay, done.
But what happens when you do that? What's released?
A
and a bunch of other particles, gamma rays, right? So overall, we could say that the sun has to be increasing in entropy, period. Like, even though it's a highly localized amount of matter that is then like even further being fused together and being organized and structured, the net effect of the sun existing is that there's more disruption to what's going on not in the sun. Okay, the way that we quantify this is through the fact that entropy is related to the number of energetic microstates of the system. So let's look at this gas diffusion example. We can tell from just looking at this, right? Gas diffusion, we are taking an ensemble, a cluster, a population of gas particles that are all located in one space. And then once we open this valve, we now have a higher degree of dispersal, more chaos. But how does that relate to like energy in general? Each of these particles could be described by its own microstate that relates to its position, its kinetic energy, its rho vibrational energy, etc. So looking at case A versus case B, which one has like the maximum number of microstates available to this population of molecules? So we're thinking like combinatorics, stats. Brianna, what do you think?
Between the two.
Yeah, between A and B.
Which one has the
Most number of microstates, the highest amount of disorder.
B?
B.
Yeah.
And that's because I have more space in which I can find a particle at any given time. So like I can consider the state where I've got all my particles over here, or I've got my particles evenly dispersed, right? The ways in which I can take one of these molecules and move it around inside this system is way more numerous than the ways I could take this particle and move it around inside this one. So there are more arrangements of particles that are possible in state B. This is why we recognize it as being one that's more entropic, more disordered, more chaotic. Let's look at an example of this, and then I will stop for the day. So here on the left is a very simplified version of what I showed you on the previous slide. We are looking now at a 2-particle ensemble. And if we were going to like think of every single possible combination in which these particles could exist, I've got state 1, where they're both on the left. State 2, where the blue particle goes over to the right. State 3, where my green particle goes over to the right. State 4, where both particles go over to the right. And even then, there's a bunch of other states because I have more room to draw all of these different blue and green dots in. I can put them higher, lower, further right, further left. So the higher the number of microstates, the more entropy your system has. So we call this the Boltzmann equation. So we quantify S via the following equation. Entropy is equal to K times the natural log of W, where S is entropy of the system, disorder in the system. K is a constant called the Boltzmann constant. This has a known value of 1.380 times 10 to the negative 23 joules per Kelvin. Ln is the natural log. And W is the number of possible energetic microstates in the system. So let's think about this. If I make the number of microstates bigger, then what happens to this natural log term? What's bigger, the natural log of 2, the natural log of 3? Yeah, whip out a calculator, prove it to yourself. Mia? Of what? Yeah, you increase the argument in the log itself also increases. So then if this whole term gets bigger, what happens to entropy? It also gets bigger because notice this is a y is equal to mx relationship. This is a direct proportionality between entropy and the natural log of number of microstates. So as you increase the number of microstates, then you are increasing the amount of disorder in your system. This is also why earlier I said that we're going to make a distinction between like material equilibrium, material reversibility, and thermodynamic reversibility. Thinking about something like this in real life. If I wanted to move this green particle over here, I let it diffuse over, and it's found in this position, so we're like looking at microstate 3. I could reverse that, like I could move my green particle back over, but realistically, am I going to be able to move it over to the exact original microstate it existed in? Meaning it's like exact position? No, we can get it over on the left-hand side, so we're close, but we're not going to be able to recreate its original energetic state perfectly. Why do we care about any of this? I mentioned it on the previous slide, but we didn't really talk about it, so I'm going to just highlight it. It's time for us to introduce a new law of thermodynamics. What was the first law, by the way? Jose, you questioned me about this earlier. Yeah. Energy has to be conserved, meaning it doesn't like disappear into nowhere, nor does it magically come from nothing. It's either transferred from one object to another or transformed from one type of energy into another. Energy is conserved. So how does that matter now? The second law of thermodynamics states that while we can look at chemical reactions or processes that increase the amount of order, meaning they have low entropy, like we do that all the time. We've seen precipitation reactions forming a solid out of more chaotic liquid, right? Rusting, forming solid rust out of gaseous oxygen. Those systems can only happen because the net change in the entropy or disorder or chaos of the universe is always increasing. So if I, the system, am going to cause more order in my locale as the system, then that means as a result, around me, the universe must be getting more chaotic. Another way to think about this is that in general, energy will always spread or disperse. There's no such thing as like stable concentrated energy. Think about thermal energy. If you leave a cup of hot coffee on the table and you come back to it at lunch like, oh, I forgot my coffee. Is it still going to be hot? No. All that thermal energy that was located in your coffee system has dispersed out into the surroundings. That's because of the second law. All right, one last thing. Is this the one? Nope, just said that. This. One last discussion. How many of us are bio majors again? Like most of us, right?
Yeah.
Or health science majors, something involving things that are alive? Yes? Okay. What does life do, Yatara?
Would this be the endocrine system?
Would what be the endocrine system? I don't know. Explain what you mean. I am not a biologist.
It's kind of like when the body like regulates itself to bring it back to
Yeah, okay. We can't just constantly run it hot. If we do, we die, right? Cells don't like to be at high temperatures.
And they don't like to be at cold temperatures either. Because while we humans as mammals have our own heating and cooling system, it cannot be prevented forever. Because if it gets too hot, then that can get a problem. And if it gets too cold, we'll freeze to death.
Exactly. Hypothermia is a problem too.
It's just like with what happened with the people from the Titanic when they jumped off.
Yeah, that is true. That's also why you shiver when you're cold.
Yeah.
Do you know what your body's trying to do?
That's just our automatic response of just trying to get warm because the shivering causes friction and that causes heat.
Okay. So I don't know if the endocrine system is like the answer to this. Because let's think about the endocrine system, right? You said that's the human body's means of regulating itself thermally, right? What would you say about the amount of disorder in a system that, like, its whole job is to regulate something?
Could you rephrase that?
Evan, what do you think?
You would want to lower the amount of chaos.
Right. In fact, I would argue it's not just the endocrine system that operates on like a very structured, first this path, then the cell does this, and then this. It's all life. That's what life does. Life takes things like high energy light from the sun and converts it into molecules, right? Life is innately something that creates order in itself. Think about a cell versus like just little micelles. Like I could have a bunch of like random phospholipids, but if I then organize them into a bilayer, now I have some kind of structural organization. I have like decreased the entropy of that system. So then how is it that life exists in the universe? Aren't we all decreasing our own local entropy? How is that not a paradox? Who, what, Ivan? Louder?
We eat food.
Okay, and what do we do when we eat food?
Yeah, calories.
And?
Energy.
Okay, so we're consuming energy from the environment. But then, like, what is the function of your stomach? It takes big, organized macromolecules like carbohydrates and proteins and such and breaks them down into smaller little bits. Yeah? Okay, that innately is increasing the entropy. Big particle goes into a lot of little ones. Evan?
But then during uptake of nutrients, when you want to lower entropy again
Yeah. So then we take those nutrients and we are processing them through some cellular metabolism mechanism. I don't know what it is. I'm sorry, I'm a chemist. So we're still at this seeming paradox. All life creates order. I am an organism. I am ordered. I have form, and that form dictates function, right? My cells are formed or organized in a particular way that tells me like what they do. That's what biologists' like whole degree is. Structure is function, right? So then how are we all here in this room talking about entropy if we ourselves are lowering our own entropy constantly? We're constantly trying to keep our temperature low.